Thank you for joining me today as we go through and we'll try to prove this theorem. That is, we want to show that if a and b are integers and n is a natural number, then we have that. If a is equivalent to b mod n, this implies that a squared is equivalent to b squared mod n. Now, as we want to write this proof, we want to keep in mind that we're going to prove this theorem using a direct proof. So that means we assume the if part and show the then part, and then we're going to only use definitions as given to us in the book, and we're going to use the lemma, let a, b, and z, and n and n, then a is concurrent to b mod n if and only if n divides b minus a. So our goal will be to come up and write a proof for this, given only our definitions and this lemma. So as we prepare to do this proof, the first thing I want to do is go through and rewrite the theorem using symbolic logic, so that we can understand exactly what it's saying, so that we're clear on what we actually are trying to show. And so, in order to show this sentence using symbolic logic, what I want to do is pay attention to, well, what are the variables in the situation? And so my variables are going to be, I have a and b, which are integers, and I have n, which is a natural number. And so for any of these, for any a, b, or for any n, we're going to have to show that this, which is if a is congruent to b mod n, then a is squared is congruent to b squared mod n. So now as I parse through that, I have my variables, but now I want to look at this and say, okay, well, this is a statement based on those variables. So I'm going to focus on just this portion, and I'm going to say my first statement is p of a, b, n is the statement a is equivalent to b mod n. So that is my p here is just a is equivalent to b mod n. Now my next simple statement is the q, so I'm going to say q of a, b, n is the statement a squared is equivalent to b squared mod n. Now if I combine these together where this is my q, this is my p, notice that they're connected using an if-then. So what I'm going to have is, I have to show the statement if p, then q. Now not only do I just want if p then q in a specific case, but I want that for any integers a and b, and any natural number n. So what I want to say here is for all a and b and z, and n and n, we have that if p of a, b, n, then q of a, b, n. And so this is the statement that we have to show, that for all of these, we have that this if-then statement is true. Now, when is an if-then statement true? Is that it is true if either p is false or q is true, or in general, we're going to say that this is true as long as whenever this is true, this is also true. So in order to prove this theorem, what we have to do is, well, whenever this is true, we have to show that this would also be true. And so what we can do is we can assume that this is true and show this is true. If this is false, then the statement's still true, so we don't have to worry about those cases. It's just when this is true, we have to show that that's true. Now that we have our theorem written out symbolically, what we want to do is we want to focus on the pieces and make sure we understand what each of the pieces are saying. So first off, I said for all a and b and z, so what is z? Well, z is the set of integers. And so what is the set of integers is all of the positive and negative whole numbers. So what we're saying here is that a and b are in the set of integers, so what we're saying is that a and b are either positive or negative or zero, and whole numbers. If we continue with this, we said that n was a natural number, so, well, that is that n is the set of natural numbers. So little n is a natural number, so what does that mean is that, well, the natural numbers are the counting numbers, so what we get is that n is a positive whole number, So we would say little n is a positive whole number. now we're working our way through, we're writing down the definition. So we said, okay, this is for all, so that means for every a and b. So any choices of a and b as integers and any choice of n as a natural number, we have to show this is true. And then we define what the integers and natural numbers are, so we'll move on and say, well, what does it mean for a to be congruent to b mod n? And so what that means is, the definition we're using is that a is congruent to b mod n if, when I divide a by n and b by n, I get the same remainder. That is, if I write a is equal to q1 n plus r1 with 0 less than or equal to r1 less than n, and b is equal to q2n plus r2 with 0 less than or equal to r2 less than or n, then r1 is equal to r2. So if we subtract off as many types of n we can and get it down so that we pick an r between 0 and n, then what we get is a is q1 n plus r1. If we do the same thing for b, we'll end up with the remainder there as well. And so we say that a is congruent to b mod n if these two remainders are the same. So now if we look up here, what we're saying is, well, we're going to assume that if we do this division algorithm and we take a and write it as q1 times n plus r1, and we do it for b as well, in both cases we're going to get the same remainder. That is that r1 is equal to r2. And so we're really trying to say, okay, well, what does this say? Is, well, we're going to be able to assume that. Then what we have to do is look at, what does a squared congruent to b squared mod n? Well, that's going to be the same definition because we're still using mod n, but we're going to work with a squared and b squared. So if I take a squared and divide by n, the remainder will be the same as if I take b squared and divide by n. And then that's the then part. So again, that's what we're trying to show. Now that we've symbolically written out the theorem and looked at all the definitions we needed from there, we're also going to look at the lemma that was given to us, because the lemma was given to us, we're probably going to have to use it. And so now as I write down the lemma in symbolic logic, what I have is, well, I have that for any a and b and z and n and n. So a, b, and n are going to be my variables. I'm going to have the statement a is congruent to b mod n, the statement n divides b minus a, and so I wrote down p of a, b, n is a is congruent to b mod n, and q of a, b, n is n divides b minus a. And what we see is that for all a and b that are integers and n natural numbers, we have that p, if and only if, q, and so we have the biconditional connective here, and so we would say that p is true whenever q is true, and q is true whenever p is true, and they're both false, so either both are false or both are true. So what we have is that p and q are equivalent to each other. So now, because we get to assume that, what that's saying is that if we wanted to show p, we could instead show q. If we wanted to show q, we could instead show p. And as this is a lemma that was given to us as part of the problem, we're going to assume this is true. And while we could go through and prove that, we're going to leave that for another problem so that we don't have to do as much within one step. Now that we have written out what our lemma is going to be, we also have to find any definitions that need to be written out from that portion. So now we had already defined a is congruent to b mod n as, if I divide, I have the same remainder. So what does n divides b minus a mean? Well, in general, what we get is that a divides b if there exists an integer k such that b is equal to a times k. So that is, if we can find an integer that we multiply a by that integer, we get out b, then we would say that a divides b. Now, in this case, because we have n divides b minus a, what we're saying is that there exists an integer such that n times that integer is equal to the difference of b and a. Now that we've taken the time to write out what the theorem was in symbolic logic and what the lemma was in symbolic logic, and we've written out all the definitions and we've composed those together so that we have a nice list of things that we need, what we're going to do is now we're going to start off with the proof and say, well, the if part was if a is congruent to b mod n, and the then part was a squared is congruent to b squared mod n. So in using a direct proof, we're going to be able to assume this, and we have to show this. So what I'm going to do is make a nice table and say, okay, these are the given things. These are the things I need to show. And so what I'm going to do is I'm going to start with this and write any equivalent statements to this. Also, I'm going to start with this. I'm going to write any equivalent statements to this. So then my goal is to get a nice list of things so that I can pick one of them and I can start here and get over to here, so that because these are equivalent, I can make over here, and then I can go back up to the original. I've shown that if this is true, then this has to be true. So I'm going to start off with a is congruent to b mod n. Because we were given the lemma, we're probably going to have to use that. So this means that n divides b minus a, and so these are equivalent to each other. So I make that into my list. The next thing is, by the definition of divides, we have that this means that b minus a is equal to n times k for some k which is an integer. Alright, and so we have b minus a is n times k for some integer k, and so now we have these three things are equivalent, and then at that point, is there another way to write, well, this divides that, and so I'm going to say, okay, well, let's stop there and let's go over to the need to show portion, and let's see if we can rewrite that. So now that I have a squared is congruent to b squared mod n, if we use our lemma, this is equivalent to saying n divides b squared minus a squared. And so if we use the definition of divides, this means that b squared minus a squared is equal to n times, let's say, k2 for k2 and z. Now I'm using a k2 because I used a k over here, and I didn't want to confuse them as necessarily being the same, so I'm using different letters there to denote that they could be different. Now again, I get to the point where I can't list anything else out that is equivalent to it. This was just using my lemma, using the definition, using my lemma, using my definition. And so what I have to do is I have to find a way to get from this column to this column. So can I think of some way to connect these ideas? That is, can I use these in order to show one of these? So now I'm going to sit and I'm going to think about that one, and I'm going to look at this, and then I'm going to say, well, what I have here is I have this b squared minus a squared. Can I do something with that in order to get out something that looks like this, so that I can use this to get out, again, that it's going to be equal to this side? So that is, if I want to show this, what I'm going to do is I'm going to start with b squared minus a squared, and then hopefully I can rewrite this using some algebra, so that eventually I get something that looks like this by using the things in my left-hand column. So now as I look at it, the first thing I would try is, well, I have a difference of squares here, so I can factor that using properties of real numbers, and that becomes b minus a times b plus a. So I know that b squared minus a squared is b minus a times b plus a. And so now if I'm looking at this, notice that, well, what I set up here is b minus a is n times some integer. So this is n times some integer times b plus a. Now what I want to notice is that this is n times this portion here, but k times b plus a is, this is an integer plus an integer is again an integer, multiplied by k, which is an integer, is again an integer. And so what I can do is I can call this k2, for example, and then what I get is that this will be equal to n times k2. So I'm going to replace this with k2. So what we've seen is that by factoring and then substituting in b minus a as n times an integer, we get that b squared minus a squared is in fact n times an integer. Well, because that's n times an integer, that means n divides b squared minus a squared, which gives us what we were looking for, that a squared is congruent to b squared mod n. So that's the outline of the proof. That's what we want to write down, and now we just have to go through and actually write that. Now as we start our proof, we want to go back through all the things that we've talked about and put them all together in some type of coherent paragraph. And so what I'm going to say is, well, we started off and we said let A and B be integers and n a natural number. So now I'm writing out integers and natural numbers just to point out that yes, we are turning this into a sentence. So we are using the original let from the theorem, and so we have A and B are integers and n is a natural number. So the next thing we need to do is the if part was, well, we'll assume the if part. So assume that A is congruent to B mod n. In the end, what we want to show is, therefore, A squared is congruent to B squared mod n. So now we're going to combine all the stuff we've written down previously to get to that. So what we said was, okay, well, if A is congruent to B mod n, then n divides B minus A by our lemma. So again, the lemma was given to us, we're going to use it, so we're going to state that we're using it. And so because A is equivalent to B mod n divides B minus A. That is, next we said that that means that B minus A is equal to n times, we'll say k1 for some integer k1. So, as we stated, we had B minus A as n times some integer, and so we want to write that out so we can provide this connection. And now what we had is we went to, okay, well, to provide the connection to get to the other end, we use some algebra. So we're going to start off with, we see that B squared minus A squared is equal to B minus A times B plus A. For the same reason that we said before, I'm just factoring it out. And then this is equal to n times k1 because I'm substituting it in, times B plus A. And so we said let k2 equal k1 times B plus A. Then k2 is an integer, and we get that B squared minus A squared is equal to n times k2. So we noted that this is an integer, so this is n times an integer, so therefore, hence, n divides B squared minus A squared. So A squared is congruent to B squared mod n by our lemma. So notice now we've connected the ideas that we've had, we've written them out in a logical progression using sentences and paragraph forms so that we started off with if A and B are integers and n is a natural number. So assume that A is congruent to B mod n. Then we know that n divides B minus A by our lemma. That is, B minus A is n times an integer for some integer k. So we see that B squared minus A squared factors into B minus A times B plus A, which is then equal to n times some integer, because that's what this is equal to, times B plus A. So we let our new integer be k1 times B plus A. So we know that B squared minus A squared is n times an integer. So n divides B squared minus A squared, which then by our lemma gives us our original proof. And so we started off with the if part of our theorem, we showed the then part of the theorem, and so this is now a proof that our theorem will always be true. Thank you for joining me today as we work through the proof of this theorem. I hope you enjoyed it, and I hope you learned something along the way. If you did, make sure to click that like button and to subscribe to the channel. There's more resources available in the description below, and also check out our other videos.